So yeah, probably we can start now. Uh, right. So just to know if my audio works fine, like could you able to see the screen and could you able to hear me? Uh, Hello. Yeah. Could you able to hear me? Okay. Thanks. So, right, we can begin now. Right, this is your week 6 problem solving session. Uh, so you will have then two more problem solving sessions from here on. We are coming to the end of your course. So there are a few more topics left, but they are really important. Uh, like uh, in regard to whatever you want to have uh, I mean in regard to the things that you want to know in physics or particularly in quantum physics, that would be very essential if you cover the later topics of this course. And yeah, you will be benefited a lot. I mean, you will benefit a lot from here. Try to go through the topics which are already uploaded on your portal. I think even week 7 or week 8 lectures are also uploaded, or maybe week 7 lectures are uploaded. So go through them and also try to solve the assignments. And also, there would be an examination for you, like for all those registered candidates. So you will be having an exam. And yeah, after that, after as I said, we would be having two more sessions. This problem solving session, there would be one more additional problem solving session as well, which would be most probably after week 8. So where that is like like the penultimate, or rather would be the final session of our usual meetings. And there that is like right before maybe your final examination that would be on this course. So we can meet there and discuss if there is any immediate or urgent doubts. We can discuss during that time, or even, yeah, you can say any doubt right during this time also. Like we have 2 more weeks, and including what we will discuss today. Yeah, but that would be just before your exam, so maybe something could be there in your back of your mind. So please feel free to join that meeting and try to uh, yeah ask any doubts if you have. And yeah, any other issues regarding this course, and any understanding, any issues with problem solving in your assignments or something. If you are having a difficulty, just let us know. So we can begin with today's topic. So that will be on perturbation theory. So uh, right. So what is exactly perturbation theory, that which you have gone through, or you have heard of, or at least I mean, if you have peeked through the lectures which are already there in your portal, or if not, then is there something I can let you know that perturbation theories is quite essential in order to study any real life physics. So it's like any practical systems that you see around, whether it's classical systems, or rather any quantum systems as well. Uh, Everything includes something non-linear term, something other than the system that you have learned through this, you have learned until this far. In quantum, so far in quantum systems, you have gone through harmonic oscillator system, you have gone through infinite well systems. So like are they really the I mean are they really the natural systems, or the systems that you come across in your real life? Well, it is not. Uh, 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 the reason is straightforward, that like, you see in real life the systems are really complex. So you see many kind of interactions with the system. So whether it's in a classical system, like when you talk about a simplest system, like even it's a simple pendulum system or any gravitational system, so there is always something additional interaction coming from the environment, coming from any third party resources. So by that it basically means if you just consider a simple pendulum, so you only consider gravitational interaction in that system, and there is nothing more. But in reality you can have a drug, you can have some other field source, could be some magnetic field or electric field, or something more. So is or something physically, some other individual interacting with the system, or something even like there can be n number of n possible of n possible ways of interactions. So yeah, so all those additional interactions that come into account in your system are basically some external source that you have to consider in your prime system. So your prime system is basically, let's start with a notion, or start with a understanding of your harmonic oscillator system. So you know your harmonic oscillator system, so it's given by some Hamiltonian, which has kinetic energy and the potential. So and that Hamiltonian, let's you call that as something, yeah, this that is H naught, that is your unperturbed Hamiltonian. Let's say uh, harmonic oscillator. So harmonic oscillator Hamiltonian, that you can denote it as H naught, which is something half m. Uh, yeah, that is just the kinetic part, uh, e square over 2m plus, or rather, yeah, half m omega square x square. But in reality, you will not just have this two terms in the Hamilton. There can be some external source. If it is some external source, is some electric field, then that can be some charge time, uh, um, uh, electric field multiplied with your x coordinate. So that is like the energy uh, uh, for the corresponding to the external field, or something. Even you could have some other form, like this is linear in x, then can be something uh, quadratic in x, that is like x square, or something more. So these are all part of your external source, or something which is not inherent to your natural quantum system. So these two terms naturally comes from your uh, or this is basically the intrinsic part of Hamiltonian. But these are some external interactions, or external uh, 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 cause that is, uh, affected due to interaction with the environment or something else. So in this case, what we are going to see, that we will deal with this kind of external interactions, where you will find that their contribution is less, in the sense that the constants that is appearing right here. Um, these things you would have seen that in your lectures, you will find that instructor would have said this already to you, that the strength of the external parameter would be very less compared to the intrinsic strength of the Hamilton. So intrinsic, when I say, it's basically related to H naught. So when the strength of the external environment is very less, then you can treat uh, your external source as some kind of perturbation. That is, you can call this part of your Hamiltonian as something HP, and this is your H naught. So yeah, so this is your total H. This is your H naught. Yeah, uh, this is your perturbed part of your Hamiltonian, perturbing Hamiltonian. So here, this is the condition that I was talking about. So your perturbing Hamiltonian should be something epsilon H prime. So as I said, if your HP has uh, minus E of x, then you can say that uh, uh, HP equals to epsilon H prime. So this is basically this is your epsilon, uh, and this epsilon you can see that it should be very less than 1. Only in that situation you can uh, treat your system as some perturbing system. Otherwise, if the strength is more, it is not if it is not meeting this condition, that is epsilon very less than 1, then you have to treat as not as some perturbation, but something as like some significant contribution is there. So you have to start from Schrodinger equation from the beginning, and you have to solve. There will be no so you will find that like in this perturbation theories, like we basically uh, we do some sort of Taylor expansion, and then we up to linear order, or some or some initial up to some leading order, like we consider the terms, and thereon we ignore it since their contributions diminishes as we go on. So but that would not happen if you are considering some significant external field which is not meeting this condition, that is epsilon not very much less than 1. So in that situation you have to you will not do some kind of Taylor series approximation, and and because of that you will not have this perturbation theory. In that situation you will start from you will start everything from the scratch. You will define without any approximation during when you have real external field contributions. A complete external field contributions. There is no small contribution. So here, like the this uh, additional part of Hamiltonian that you see, which we are calling as part of Hamiltonian, they're actually small. But even if they are small, they have very significant change in dynamics in terms of energy spectrum, or or in uh, or in other aspects as well. So that we will try to see that. So how we can see or we can uh, include, or we can quantify the effects of this perturbing Hamiltonian. So for that, right, yeah. So you have a Hamiltonian system. Let's say some Hamiltonian system whose eigenvalues are given by En, and eigenstates are given by psi n. If you expand that, mm, um, or basically uh, um, uh, uh, this Hamiltonian H is basically the total Hamiltonian, which contains both uh, H0 plus HP. And for this complete Hamiltonian, your eigenvectors are psi n, and for this complete Hamiltonian, your eigenvalues are En. uh, and you can write this psi n as some this is basically the eigenstates corresponding to total Hamiltonian. So this is your total Hamiltonian, total H, total H. So corresponding to your total H, the eigenvectors are denoted as psi n, and you can say that psi n basically contains the original, or basically the unperturbed. Uh, this is unperturbed eigenvector, and these are your perturbed eigenvector. First order, you can say that this is your first order perturbed eigenvector, first order perturbed eigenvector, and this is your second order perturbed eigenvector. Right. So again, you have total energy. That is the energy of your corresponding to total H, corresponding to your total H, and these are your uh, uh, corresponding your corresponding to total Hamiltonian, which contains both perturbed and the unperturbed part. So that energy eigenvalue, you can split into your unperturbed energy eigenvalue. This is unperturbed, and these are your perturbed part of your eigenvalue. Due to the perturbation, you have additional uh, energy eigen. So, for example, when I was talking about harmonic oscillator, so harmonic oscillator, like as I said, um, uh, uh, yeah, corresponding to this H0, you have something uh, En0, the eigenvalues, uh, and you have something eigenvectors psi n0. These are your unperturbed parts. So um, yeah, like uh, let me just maybe, so these are your perturbed part. So yeah, so for if H naught is your uh, if your harmonic oscillator, so you have psi n0, the eigenvectors of your harmonic oscillator, and en0 are the eigenvalues of your harmonic oscillator. So uh, but when you have some perturbation to this, if you add some perturbation, add perturbation, then your psi n0 then will become, psi n0 will become something psi n0 plus some correction. You have to apply correction due to because of additional perturbation. So similarly, you have to add something on en0. Uh, uh, I mean en0 will also become something epsilon en correction. Yeah. So basically, I mean uh, like your energy eigenvalues, like for en0 for harmonic oscillator, you can write it something uh, n plus half, or basically something uh, n tilde h bar omega. So you will not find like in a linear harmonic oscillator system, a linear yeah, right, fine. Yeah, no, that is some other issue which we will talk about in a few moments. But yeah, energy eigenvalue of a harmonic oscillator is something given as n, is your quantum number, uh, that is n plus half times of h bar omega. uh, so when you have perturbation, that will change as something your total En will change to something n plus half h bar omega plus something more you will have, like you will see that something times h bar omega and so on you will have. So this will be like your first order correction, and more order will be there. So it's like whatever your original states and energies were there, they will still going to remain true, but with some additional corrections. So the I mean, excluding your unperturbed part, rest additional terms that whichever you will add on to your eigenvectors and eigenvalues, they will be your corrections. So the corrections are given as, so like for first order there are we will consider up to second order corrections, like you will add two terms in your eigenvectors and also in energy eigenvalues, and you will find the other like when you will do this complete derivations, you can find that the uh, other higher order terms, like they will diminish further, because one thing which we have been considering so far in all these cases is that this epsilon is very less than 1. So you will find that the other higher terms will go away, but still the first but including, but it's not obvious that they will always diminish. For some cases, like even third order would matter, and is the idea is like the more orders that you put in, the more you can accurately model your system, and that would give more insights. So far the important features that we wanted to know, like in various real life systems, we can exploit it right by just including first two orders of correction, and you can also probably get something more in third order. But yeah, but as we go on more and more higher orders, like think the fx will basically the contributions would basically um, I mean would basically reduce more and more. So it's like you can see epsilon squared, then your epsilon cube, epsilon fourth. So epsilon is very small itself. So right, and the corrections which I was talking about. So in energy eigenvalue, the this en this thing. Uh, uh, the first order correction in energy eigenvalue is given by this. So you take the h prime, that is your perturbed Hamiltonian. This is your uh, this is your perturbed part of your Hamiltonian. This h prime. You can see this h prime is here. So this is your part of your perturbed Hamiltonian. So you take the expectation value of that perturbed Hamiltonian in your unperturbed eigenstate. So that proof again, when you will do the derivations, you will find out, and probably this will be already done in your lectures. You can check that out as well. So this is how the first order correction is given. So this is something important we'll be using often in our today's problems. And further, if you want to do second order correction in energy, so this is something a bit more uh, uh, addition to your unperturbed energy eigenvalue, which goes as something. So these are your energies. Let me, yeah. So again, you take your unperturbed part of a Hamiltonian, you take the expectation in uh, like in your unperturbed eigenvectors, uh, and the eigenvectors like which you will consider, like they will not be exactly same eigenvectors. I mean, in which you will take the expectation, they are different. M should be not equal to n. So it will be clear if, when we will do an example right just away. I mean right away, which we will be doing right here. So yeah, but this is what the second order correction is. And the correction to the energy eigenstates are given something as this. So the f- uh, so this correction is similar to the correction in second order of an energy eigenvalue. So again, like, we'll do this how this works out. So suppose, like, if you consider this case, uh, so it's clear, or anything, any problem with this part? Like, this is just a preview that I wanted to give before diving into the problems, where we will be using this key relations to find out the actual features of the perturbation theory. Yeah, like, anything, any issue, or is it fine? Is it clear for you? Okay, thanks. Um, okay, so yeah, the first thing, like, is on the infinite well potential. Uh, okay, so uh, a, a particle of mass m is confined inside a box with boundaries x equals to plus or minus L. The ground state and the first excited state of this particle are E1 and uh, E2 respectively. So then there's something more, the perturbation, a repulsive delta function is introduced. So this is basically your perturbation part of your Hamiltonian, lambda times delta x at the center of box, where lambda is within 0 and this value 32 over m, 1 over 32 m, h upon L square. So you will check that, I mean, this is to ensure that this lambda is very small, such that you can treat your total Hamiltonian as some perturbative system. So then the uh, question goes as, if uh, E1 prime and E2 prime denotes uh, new ground. So these are your new ground state. So new means your total uh, uh, new ground state energies, and so new ground and first excited state energies. So these are your total ground state and your total first excited state energies, which includes both your corrections and of course your uh, original or unperturbed uh, eigenvalues, unperturbed energies, energy values. So then compare E1 prime and E2 prime uh, with their unperturbed energies. That is E1 and E2. So E1 and E2 are the unperturbed energies. So let's maybe denote this as E1 0 and E2 0. So right, so the thing is like just you have your usual infinite well potential infinite well system where uh, the system ranging from minus L to plus L, and so this is like a symmetric infinite well system where the ground and first excited states are, let's say, given by E1 0, E2 0, and then on top of that, on top of your infinite of your original infinite well system, you have a perturbation lambda delta x. Uh, so it's like you have your total Hamilton. You have something total Hamiltonian H as H zero plus uh, let's say H prime, and so your H zero is basically p squared by 2m plus v v zero x, where v zero x is uh, zero between minus L, uh, yeah, between minus L and L, and then you have uh, infinite otherwise. So, right. Uh, and your H prime is basically something V prime X, uh, where V prime X is uh, V prime X is lambda times delta X. So, and delta X, that is your delta function. So, that is delta X. I hope you are familiar with it. That is infinite when you have uh, x equals to 0, and otherwise it is 0. So your Hamiltonian is something this e square over 2m plus uh, v0x plus lambda of delta x. So this is your system, right? And corresponding to this system, your uh, let me just slightly change the notation in the question. It is, or yeah, maybe, or let's say uh, like in the question I'm just changing this e1 prime as e1 and 2. So right. So your originally your energy eigenvalues were E10, E20, but after the perturbation, your new eigenvalues are E1 and E2. So which you have to calculate E1 and E2, right? So your original eigenvalues now, uh, like your new eigenvalues, which are E1 and E2, now they will go as something E10, which is your original unperturbed energy eigenvalue, then plus some lambda times uh, E1 prime plus lambda square times E1 uh, 2. So this is your E11, this is your E12 plus you have higher lambda cube E13. So this one basically denotes your first order energy correction, first order. uh, this basically tells first order, second order, and this is basically your first order correction in your energy eigenvalue, first order correction in energy eigenvalue, right? So then you also have the uh, other energy eigenvalue, that is your first excited state energy. This is your ground state energy, and this is your first excited state energy. So your first order excited state energy will again have the same trend. So that is E20. Then your first order correction will be something lambda uh, E2 superscript will be 1 and lambda square E2 2, and so on. You will have other higher order corrections, so which we are not considering here. So now to calculate the first order energy eigenvalues, so first order, uh, it means this and this. So the first order energy eigenvalues, you can calculate it from the relation that we discussed at the start. So we this is your first order correction. uh, this is your first order correction in energy eigenvalue. So this is a correction term. Note this. This is your correction term. So this correction is goes by this relation. You have to basically calculate this expectation value. You take your perturbing Hamiltonian H prime and you sandwich it between your unperturbed uh, uh, energy eigenstate. So so what is this for our case? So we have uh, so from that relation, if I write it down, E n prime is psi n 0. Psi n 0 is basically your so suppose if I write down the, let's say psi n 0 will be let's say psi uh, let me create a space here. Okay. So here I just wanted to tell you that what are the changes in your eigenstates that you will find after this due to this perturbation. So for eigenstates, you will have psi n as something psi n 0 plus lambda psi n 1 plus lambda square psi n 2 plus so on. So for if you put n equal to 0, that will be ground state correction. If you put n equal to 1, that would be first excited state correction. First excited state total eigenstate, which includes the original. So let's say if n equals to 0, you have psi n 0 is uh, you know for uh, let's say psi n 0 is written as for your infinite well system, psi n 0 is written as uh, root 2 over L. Um, so this is like something, it goes like, uh, let me, uh, for unperturbed infinite well Hamiltonian, you have uh, psi n 0, the eigenvectors are given as. So remember, this is your symmetric infinite well. So symmetric infinite well, the eigenvalues are slightly denoted as a bit different. So they are like 2 over L, that is square root sine of n pi x L if you're for odd n, basically for your uh, first excited state, or your uh, like first, third, and fifth, and so on. Your these excited states, you will have sine of n by xl. Then for even uh, n, for even n, like ground state, you will have cos of n by x over l. So these are your original uh, eigenstates. On top of original eigenstates, you will have corrections. So now if you uh, right, so then you can writing down the um, correction term relation. So this is your correction term relation, psi n 0. So so this has so this is basically lambda times, because your h prime is this is your h prime. Yeah, then yeah, so this, which you can calculate for you have to calculate it for n equals to 0 ground state and first excited state. So if you take n equals to 0, then you have what is psi or um, not n equals to 0, because you cannot take n equals to 0 for uh, you cannot have n equals to 0 for infinite well. You know that, because the energy eigenvalues, they go as, I can write down E n 0. The energy eigenvalues are basically n square pi square h bar square over 2m l square. So in this case, your L is twice of L. You can see here. your L goes from minus L to L, so that is like 2L. So here there will be 2L square. So you know this N goes from 1, 2, 3, and so on. So that is why your N equals to 1, 3, they are your ground state and your uh, second excited state, and like that you have uh, fourth excited state. These states you will have this eigenfunction, they are odd in n, and for others you will have cos of n pi x over n. So yeah, so for we have to calculate for basically for not n equals to 0. Like if you have a harmonic oscillator system, there n equals to 0 is allowed, but here uh, which you know already that n equals to 0 is not a case in uh, infinite well. So you have to take n equals to 1 for ground state. This is your ground state. N equals to 1 denotes your ground state of your infinite well system. So for n equals to 1, your uh, psi 1 0 is basically given as what? That is given as psi 1 0. If you calculate for even, that is your uh, it's for probably there is a little confusion right here whether this odd and denotes sine or even and denotes cos. Let me check it quickly. Just in a minute, I'm just checking it. Yeah, so there was a small error here. Uh, so apologies for that. So that is not actually uh, even. I mean, for this square root 2 over L sine of n by x over L. So that is valid only for even n. So initially I wrote it as odd n, but that is valid for even n, and for uh, this is valid for odd n, right? Yeah, sorry for that. Yeah, for odd n, we can write down. Um, you can write down our ground state as something. If you put n equals to 1 here, n equals to 1 is odd, that means you have to use this uh, cos function, that is cos of pi x over L. So your wave function is root square root 2 over L cos of pi x over L. So you got your psi 1 0. Then you just have to calculate this expectation. Uh, so you can easily do that. You know your unperturbed ground state eigenstate. So then for n equals to 1 you have e1 1, that means first order correction in your ground state energy, that is lambda times psi n, so psi 1 0 delta x psi 1 0, that is basically you calculate it your in, in integral. This is how you can write down your expectation value. So minus L to L is your size of your infinite well system. So psi 1 uh, bra of psi 1 0 is psi 1 0 star. It's basically complex conjugate um, delta x, then psi 1 0. So psi 1 0 is basically this thing, and if you substitute that term right here, so again uh, for this case it is not exactly this thing once again, because your size of your infinite well is 2l, as I already told. So that is why I initially changed this factor from l to 2l. So likewise you also have 2l here, 2l here, 2l here, and 2l here. So that will be, there will be 2l, 2l. Yeah. So you can write down that as lambda over L if you substitute what is psi 1 and psi 1 star, psi 1 0 and psi 1 0 star. So that is minus L to L going, I mean, that is how your integral varies over the range. And cos square uh, pi x over 2L delta x dx. Then, right. Yeah, then if you solve this delta function, so you know the property of delta function, that you have delta x, so your peak is at x equals to 0, and your integral is I mean your peak is within this range of minus L and L. So you can write down your delta from your delta function property. This will be uh, I mean if I if you just recall your delta function property, which is something, if it goes from minus L to L, f uh, delta of x minus a f of x is basically f of a if your uh, a lies within, if a lies within uh, minus L to L, that is L is minus L a L. So like, I mean, if you if your delta function yeah, so it is like you have a I mean for this case this delta function which we have brought lambda of delta x. So how I mean this is basically effectively your perturbed I mean the total potential effect, v effective, let's call this v effective. So that how does this look like? This would normally look like this. uh, this is, let's say this is v effective. uh, so at x equals to 0, let's say this is x equals to L and minus L. These are your boundaries of your infinite well, and you have your, this is your This is your lambda times delta x. This is at x equals to 0. So this is how your b effective will look. Right. So that is what I was telling. So your delta function is within the range of minus L to L. So here in our case, here is 0. Right. Fine. So then just the integral is simply uh, lambda over L cos of 0. So that means lambda by L is your first order correction. So you can find, you can write down finally your E1 prime, or E1 is basically your total energy. So that is like E1 0 plus E1 1. That is your total energy. So that is like, so E1 0 has been initially, so for n equals to E1 0 is basically unperturbed part of your energy eigenvalue, your ground state energy eigenvalue. So your ground state energy eigenvalue is pi square h bar square 2m times of 2l square plus lambda over L. So right, then similarly you can calculate what is uh, E2 prime. So you have to calculate again the first order term. So E2 prime, if you calculate, what you will find, uh, so this is not cos of this cos square. Yeah, if you calculate E2 prime similarly from exactly from this way, in that case you just have to replace uh, psi 1 0 with psi 2 0, and again this psi 1 0 with psi 2 0. Then you will get this, this is like psi 2 0 delta x, and uh, this is like, yeah, psi 2 0, uh, this is delta x psi 2 0. This is what you have to calculate, and if you calculate, like, you will find that this will give you 0. This is your first order correction in uh, sec first excited state energy. So you will find that E2 would be E2 0 plus E2 1, the first order correction. That is like pi square, that's 2 square pi square h bar square over 2m 2l square plus 0. So yeah, so this then um, yeah, that is what you will find. These are your first excited state energies. Then the thing is like, if E1 and E2 denotes new ground and first excited energy, compare E1 and E2 with their unperturbed energy. So if you compare total E1, so E1 and D2, so you will find that E1 is greater than, in this case, so here you will find E1 is basically greater than your original E10, because you see that this lambda by L is something positive. So lambda, initially it was given that your perturbation, this lambda is positive, and L is your length is basically always positive. So this is always greater than 0. So you are adding some positive number on your unperturbed energy, original energy. So that means it is something very, I mean something greater than your original Hamiltonian, because there was some quantity and you added something on it, so it is obvious that that quantity, that overall quantity is at the end of the day is greater than the initial uh, non-added term. So that is going to be so this energy is basically greater than your original unperturbed energy. So but here in this case, for the uh, uh, first excited state energy eigenvalue, your uh, unperturbed energy eigenvalue was something e2 0, but your first order correction is 0. Since first order correction is 0, so this is 0. So that means your e2 is basically equal to your unperturbed energy. So you're including the correction, your energy is still what it was before. So yeah, that was about the first question. So if there's any problem, if there's any issue in understanding, please let me know. Uh, Anything you didn't get? Any issue, or you can move on to the next topic. Okay, so if not, let's talk about the other uh, scenario of a perturbation theory, where we will talk about some system having degeneracy. So this is what I have talked about. Is all about uh, non-degenerate. Uh, this is about non-degenerate perturbation. So that means like all energy eigenstates of your given Hamiltonian system are distinct in the sense that they have unique energy eigenvalues. So suppose if your system is infinite well system, so your energy eigenstates are psi 1, psi 2, psi 3, and so on. So for each given psi let's say psi 1 will have some energy eigenvalue e1, and psi 2 will have some energy eigenvalue e2, and so on. So these are like for each given uh, energy eigenstate psi 1, psi 2, psi 3, you have unique energy eigenvalue associated with it. So there is no it's not psi 1 and psi 2 both have energy eigenvalues, let's say something even. But that happens if your system is something higher dimensional system, like if you take consider a um, if you consider like two-dimensional infinite well system. So like what happens in two-dimensional infinite well system, if you consider let's say uh, two-dimensional infinite well system, uh, infinite square well, let's say square well system. So your um, so you will have something, your you will denote your uh, eigenstates something as uh, nx ny. There will be something uh, sine of nx by x over l plus uh, there will be some factors of constant factors alpha, let's call that alpha and beta, and sine ny by pi y over l, and your energy eigenvalue are basically something uh, nx square plus ny square plus pi square h bar square 2m L square. So you will find for if your uh, first excited state, your first excited state, uh, that means, or let's say, uh, yeah, first excited state means nx equals to 2 n. Uh, let's say what is your ground state. So ground state is basically 1 and 1, where nx equals to 1, ny equals to 1. So there is no nx equals to 0, which, as I said, in infinite well you are not allowed to have n equals to 0 case, but you see that in harmonic oscillator that is allowed, but here in infinite well, so you have for this 2D infinite well case, you have nx and ny both should be equal to 1. So for corresponding to this 1 1, your energy eigenvalue you denote as, let's say, ground state, let's call this as E ground state, is 1 plus 1 pi square h bar square over 2 ml square. But if you take, let's say, first excited state, so first excited state could be 2 1, uh, or and also 1 2. So your first excited states are both 2 1 and 1 2. How? Because if you calculate your first excited state will be, if you calculate this energy, you will find that uh, you first take 2 1, that means your nx is 2, your ny is 1, then you take nx is 1 and ny is 2. You will get the same energy eigenvalue in both the situation. So that is like, so what would be, it would be like 5 pi square h bar square 2 ml square. So this is your energy. This is the first excited state energy of your 2D infinite well or infinite square well potential, where this energy state, or this energy eigenvalue belongs to belongs to both uh, one 2 1 state, 2 1, and 1 2 state. So you can say you have two distinct states. So you have this 2 1 and 1 2, they are two distinct states, but they have common energy eigenvalue. So these are like degenerate systems. So this happens in, as I said, when you have a I mean, in higher dimensional system, this particularly happens. Like this you will not find in one dimensional system. So you never see any degeneracy in 1D infinite well. So also not in 1D harmonic oscillator. So same thing you will find if you have 2D two dimensional harmonic oscillator or three dimensional harmonic oscillator system. There also you will find this kind of degeneracy. Uh, and there are also something called accidental degeneracies, uh, which is basically due to the parameter values of your system. Like if you like, that is a different case. uh, uh, yeah, and most commonly which you have seen in hydrogen atom system, that is also something your uh, I mean, three-dimensional system where you will find this kind of degeneracy, or you will see there are a lot of degeneracies there. Yeah, so we will see there would be some problem that we will discuss today, where we will find those kind of degeneracies. So, but for this kind of degenerate system, so specifically we deal uh, this perturbation slightly in a different way, because I mean, uh, the way which we have discussed the relations that we have found out, I mean, these relations, basically the correction terms due to this perturbation, uh, due to this perturbation, we found this first order correction in energy eigenvalue. This is your second order correction in energy eigenvalue. They will not hold true if if your system is a degenerate system, like the case which I said. If it is your two-dimensional infinite well system, if it has degeneracies like that, then you cannot use this relation. So this is only valid for your, specifically for all one-dimensional systems, where you have your systems are non-degenerate. So So let's say if your some state which has twofold degenerate, like for example the case which I said here, this is your twofold degenerate, which means two eigenvectors, two different eigenvectors have same eigenvalue. So if it is threefold degenerate, there would be like one more eigenvector, let's say something 2 2, but not here in this case, because 2 2 will definitely have different energy eigenvalue. Or let's say if it would have been three-dimensional infinite well potential, so in that case it would be like 2 1 1 and 1 2 1, and then you have 1 1. These three different eigenvectors will have basically same eigenvalue. That is like threefold degenerate, which you will find in three-dimensional uh, infinite well system. Or yeah, yeah. So, but if you consider twofold degenerate here, so something we are considering a similar case where you have a two-dimensional system like a 2D infinite wells, 2D infinite square well, where your psi 0 a and psi 0 b. So basically psi a and psi b are your two different eigenstates which has same eigenvalue e0. So this all these zeros represents your unperturbed system. So we are dealing with unperturbed. So now what you can do, you write your two different eigenstates which has same energy eigenvalue, that is E0, as some linear combination psi 0. And and then if you to calculate the uh, yeah to calculate the first order correction in your energy eigenvalue, so what you have to do, basically, uh, if you remember, like we had something, if I go back to the previous relation. So our first order correction in energy eigenvalue was something like h prime. We are taking expectation value of h prime, that is your perturbed Hamiltonian, in this unperturbed uh, eigenstates. So something will do that again here as well, but there is a catch right here, because now the states are degenerate. So what is that? Uh, so to get this kind of expectation, so what you can do, so now you consider this is your unperturbed state. So you are taking your unperturbed state as a linear combination of psi A and psi b, where psi A and psi b are also unperturbed states, but they are different states corresponding to same eigenvalue, that is E0. So now you are defining your psi 0 as this. This is your unperturbed state. Now, to as I said, this first order correction is something given as expectation in unperturbed states psi 0. So this psi 0 are basically this psi 0 are not, I mean, this psi 0 is basically the psi 0 in the relation. So this psi 0 are same. So so that is what how these relations are coming right here. So let's say first you operate h prime on both sides of this relation. So you will get uh, uh, something alpha h prime psi a 0, then plus beta h prime psi b 0. Then after acting h prime, then you operate this psi um, this you operate this psi a 0. I mean, so psi a 0. So on LHS this would be something like this psi a 0. So this is like alpha, then you have beta, you have psi a 0 h prime psi a 0. So similarly, you repeat the same thing again by acting h prime on here, and then act psi b 0. So you will get two different equations like this right here. So uh, I can uh, write a small notation here, or yeah, apply uh, psi a 0 h prime on both sides of equation, on both sides, then apply psi b 0 h prime on both sides. So you will get uh, two such uh, relations. So you will see that this relation, you call this, this is some expectation value, you call this as something WA, and you call this again, this is some expectation value, you call this as something WAB, and again this is WBA, and this is WBB. So you see, you can construct a matrix relation. So from these two relation, these two equations, you can construct a matrix relation. So that is this. Uh, you can construct a matrix. This is your W matrix, and this is something like and this is something like your vector, and this is again something, the same vector that is appearing here. So it's like you formed an eigenvalue relation. So this is like, uh, I can write this as something W of x equals to uh, lambda x. So this is like your eigenvalue relation. So now our job is to calculate the correction, this correction. So this E1 basically denotes your first order correction. So our job is to calculate that. So if you see that this lambda is basically, or let me just write, this is E1. So this E1 is basically your correction. So and if you have something of this kind of relation, it is very obvious that this is your eigenvalue equation, and E1 is your eigenvalue. So it's basically uh, eigenvalue. So basically, if you take the eigenvalue of this W matrix, you will get your corrections. So in degenerate system, so basically you have to construct this W, this matrix, this W matrix. So once you have your W matrix, you take its eigenvalue, and the eigenvalue that you will calculate, that would be simply your first order correction. So that is what you just have to do in degenerate perturbative Hamiltonian system. So we'll see an example how we can do that. Uh, so yeah, so it's basically, so now this relation is basically your eigenvalue formula. So this is simple. I mean, if your matrix is given like this, then corresponding to this matrix, you will have two distinct eigenvalues, that is E plus and E minus, and this is given by this relation. This is your uh, eigenvalues corresponding to W matrix. So now this, or these eigenvalues uh, gives distinct corrections to the unperturbed or original eigenvalue. So now you will find that your initially your energy, I mean your unperturbed energy, which was E0, they like this E0 were the same energy eigenvalue for both uh, uh, for both uh, psi A0 and also for psi B0. But now you have E0 plus E plus, then you have E0 plus E minus. This will be the eigenvalue corresponding to your psi a is 0, and this will be your eigenvalue corresponding to your psi b 0. So it's like you are breaking this degeneracy. So degeneracy has been splitted, or degeneracy is splitted, or basically that degeneracy is broken. So now your system, which was initially degenerate, like particularly corresponding to this psi a 0, psi b 0, which had same eigenvalues, now they have uh, different energy eigenvalues all of a sudden when you are adding a perturbation. So that is what this uh, um, energy eigenvalues, this correction terms can do. So that is why this perturbating systems, they add a different, a whole lot of things to your existing Hamiltonian system. So that is why it is very important to know that. So right. So now, like, if there's any issue or anything, you can ask uh, Rohan, uh, Sinogita, like any questions, or is it clear, or anything, any problem? Anything not clear, please. Sorry. अच्छा, जो ये मैं डिस्कस कर रहा हूँ यहाँ पे, जो मैं यहाँ पे लिख रहा हूँ, हाँ, ये जो मैं लिख रहा हूँ ये सारे अवेलेबल है आपके, these are all available in your NPTEL portal. I mean, if you log in into portal, सो आप लॉग इन कर पा रहे हैं ना, मतलब अपने पोर्टल में, जहाँ पे सारे मटेरियल और रिकॉर्डेड लेक्चर्स भी अवेलेबल हैं। हाँ, तो उधर आपको मिल जाएगी, या फिर आपको एक ईमेल भी आता, तो वहाँ पे वहाँ पे ये सब अवेलेबल है। अभी अभी कुछ डाउट है तो पूछ सकते हैं, कुछ प्रॉब्लम है कहीं पे? ओके, ओके, फाइन। या या वी कैन discuss a question right here. Uh, Suppose we perturb the infinite cubical well by a delta function at uh, a over 4, a by 2, and 3a over 4. It's like initially how the example where we checked the delta function was at origin. Now we have a three-dimensional infinite cubical well. So this is the delta function is at this height of a by 4, a by 2, and 2, 3a by 4. So this perturbing Hamiltonian is given as a cube, V naught delta x minus a over 4 delta y minus a over 2, then delta z minus 3a over 4. So find first order corrections to the energy of the ground state and in the triply degenerate first excited state. In the triply degenerate first excited state. So, so your potential is something given as this x, y, z. So it's like your potential is zero for x varying from 0 to a, y varying from 0 to a, and also z varying from 0 to a. So it's a cubical well potential. So it's like a cubical region is there around which your particle is trapped. So that is like a cubical box inside which particle is trapped. And outside or everywhere, your potential is infinite. So where your particle cannot escape. Basically, it is trapped within a region of a cube volume. So then your energy eigenvalue is then given as your unperturbed energy eigenvalue E0 is given as pi square h bar square over 2m a square nx square plus ny square plus ng square. So it's like your if you see for so this is like for ground state. For your ground state, your energy eigenvalue is this, and your and the and your basically first write down the ground state. So the ground state should be uh, nx equals to 1, ny equals to 1, and nz equals to 1. So then your your ground state would be something psi 111. 0 is your unperturbed. So psi 111 your unperturbed state. So that is basically equal to let me write down the general for all for general nth ground state for unperturbed Hamiltonian is given as psi 0 nx ny nz xy z is given as 2 over a 3 by 2 sine nx by x over a sine ny by y over a. So sine ng or pi z over a. So I think initially I was given example of two-dimensional infinite well. So I think somewhere I have, yeah. So there is a mistake here. Like it should not be plus. It is actually a product. So that was my mistake. And yeah, and this alpha is some factor. That is fine. So that is how two-dimensional infinite square well general state should look unperturbed uh, state. So for three dimensional, this is how it is. So for psi 100, you can write it as uh, 2 over a 3 by 2 sine of pi x over a sine of pi y over a and sine of pi z over a. So corresponding to this ground state, your eigenvalue is this. So you find that like one eigenstate that is psi 0111, you have E0 eigenstate. So it's completely is a non-degenerate state. So in actual practice, you should see what is the perturbation you are calculating for a given state of your system. First, you see if the state of your system is degenerate or non-degenerate. So you see this psi 1110 is a non-degenerate state. So only has it is one eigenstate and one eigenvalue. So you can now just simply use the to calculate the first order correction. You can simply use the non-degenerate relation, that is as we have done at the beginning also. So you just have to use this relation, that is psi 0111 h prime your perturbation psi 0111. So so it's like again a similar thing you have to do, like here also you have a delta function integral like before. So it's like psi star h prime psi, but you have to do volume integral this time. And yeah, you use this so this is your first order correction in your ground state. So so this will something, if you write down, it would be something 2 over a 3 a cube v naught. V naught comes from your h prime because your h prime is this. So your h prime is this. Uh, right. Then you have three integrals. Then you have delta function x minus a over 4, delta y minus a over 4, then delta z minus 3a over 4, then sine square pi x over a, sine square pi y over a, then sine square pi z over a, then dx dy dz. So right, then you separate out integrals. So you basically you can integrate variable right here. So first you integrate the x part. So that is delta of x minus a by 4 sine square pi x over a dx. Then you will have, you integrate the y part, and then similarly you integrate the uh, z part. So from there, so here as we evaluated the delta function before, the same thing you have to do here. So this is like sine square pi over a by 4. In place of x you will have a by 4, this a by 4. So this is like uh, 1 over 2 sine square pi by 4. So sine pi by 4 is 1 over square root 2. This is, so from here you will get something, from here you will get 1, and from here you will get 1 by 2 again. So yeah, so from here you basically get your, if I write down the complete, also you have some factors outside. So by taking out everything, you get your correction as 2v naught. So that is your unperturbed part. For the yeah, that is your for the ground state. This is your first order correction. That is your right. Then you have, then you take the first excited state. Your first excited state, you will note here. First excited state is triply degenerated. Also something uh, said in the question as well. So how is it like? Let's consider uh, what would be your triply. I mean, how you say your first excited state, because your first excited state would be, uh, I mean, leaving out your lowest energy, that is your ground state. The next higher energy on that, I mean, on top of your ground state will be this thing. I mean, when you're, if you put, uh, so uh, yeah, basically here you put 1 1 1 for the ground state. So in general, your E0 and X and Y and Z is basically pi square h bar square over 2m a square nx square plus ny square plus nz square. So this is your, in general, your uh, your ground state. I mean your ground state and your unperturbed energy. So ground for ground state, your nx, ny, nz should be one, so that this is the energy is minimum. So it is minimum. Like from here, it is reasonable to see that, and if nx, ny, nz both are zero, then that will be your minimum. But that is not the case. You cannot have zero energy, because that is not allowed in your infinite well. We have seen it also. We have some vacuum energy. That is why your n starts from n equals to 1. I mean nx equals to 1 and y equals to 1 and z equals to 1. So then the next would be either one of this would be, instead of 1 1 1, either one of this could be 2. So if either one of these three could be 2, that means 1 1 2, or 1 2 1, or 2 1 1. There are three possibilities in which your energies could be same but higher than this 1 1 1 case. So that is like your first excited state energy is either 1 2 1, or 1 1 2, or 2 1 1. So that is why you have three distinct states. So it's like psi A is psi 0 2 1 1, psi B is psi 0 1 2 1, and psi C, you're denoting this these are all first excited state, psi 0 1 1 1 1 2. So yeah, so corresponding to these three, you have to basically construct this W matrix, which we discussed in the degenerate perturbation, where you have to calculate what is WAA, WBAB, WAC, WBC, WBB, WBC. So this is BA, WCA, WCB, and WCC. So so you got, and all these three eigenstate have same energy. Like they, all these three have E0, uh, E0 first excited state is basically, how much it would be. It would be, uh, earlier it was 3 times pi square h bar square by 2m, so it would be pi uh, could be 4 6. I think this would be 6 times pi square h bar square by 2m a square. Yeah, so all these three distinct states had one energy. So now, to calculate the first order correction to this first excited state, you have to calculate this eigenvalues of this matrix. So before calculating the eigenvalues of this matrix, you first have to know what are these elements. So that was your first task. So to calculate these elements, let's go. Uh, let's start by evaluating what is WAA. So WAA is psi 2 1 1 h prime psi 2 1 1. So these are your psi 2 1 1 is your unperturbed state. So this, you if you write down, it will be 8 times V naught. Uh, so you have to follow this thing like, psi 2, like I have written down the general psi here. So this is your general psi. So for psi 2 1, you put nx equals to 2, ny equals to 1, and nz equals to 1. So you put this nx, ny, nz right here. You will get your psi to 1 1 state, unperturbed state. So from there you will get sine square uh, 2 pi over ax, because your nx is 2, ny is 1, and nz is 1. Then you have the other sine square term, that is sine square uh, pi over a y, then sine square uh, pi a pi over a z. Then you have this delta factors, that is delta x minus a over 4, delta y minus a over 2, then delta z minus 3a over 4, then dx dy dz. Yeah, then the same thing you have to do. You can calculate it, like the similar integral we just calculated in the for the non-degenerate case. So this is the same integral, similar kind of, very similar kind of integral. So uh, if you calculate this, uh, so if you get, you will get something WAA right here, and same way you calculate WAB, then WBC, W, uh, yeah, you calculate what is WAA, then WBB, then WCC. Then once you calculate WABC, and you have to calculate this off diagonal AB and AC and BC, and you will find that most of the cases this AB will be same as what BA. They will be symmetric. They has to be symmetric. AC should be similar to CA, and BC should be symmetric to CB. And you will find that most of them could be also zero, like they could be odd integrals. You have to check that and see. So yeah, and after you get the full matrix, you have to calculate the eigenvalue. So when you will calculate the eigenvalue, like I'm writing down the final answer. This is just like a very basic mathematical steps you have to do. You have to like this integral is something which we evaluated twice. Like here we did once, this is the one, and the same which we did at the beginning, like that was a single integral. But yeah, but now you have three integrals to evaluate, like how we did here. So similarly you do for all this WA, WBB, WCC, and you'll find most of them will also go zero. And from after doing that, you will construct this matrix, this W matrix. This is your W matrix, and you take eigenvalue. So you take, calculate eigenvalue, calculate eigenvalue. So from here you will get eigenvalue would be your corrections in your first order correction in your first excited state. So this is like your first excited state. So you will get 0 0 and 8 times of v0. So basically then you can say your psi 2 1 1 has energy E0 plus 0. Then psi 2, psi 1 2 1 energy has E0 plus 0. And your psi 1 1 2 has energy E0 plus 8 V0. So now you see initially your, it was a threefold degenerate, triply degenerate, which we initially show here. It was the triply degenerate state where all of the energies were this thing E0 first excited state. So this is a your E0 first excited state. Let me write down, this is your first excited state. These are your all first excited state. All of them were having same first excited state, E0 first excited state. But now the third one has different energy, but the first two has still has the same energy. They are still first excited state, but the third one has some contribution due to the perturbation. So now from threefold degeneracy, you brought it down to twofold degeneracy. So you have somehow splitted this higher degeneracy into three. So uh, somehow you have again broken the symmetry here. So that is what we were discussing here in this degenerate perturbation theory. That is what something very interesting happens. This is what I was claiming before, right? That this should happen. Degeneracy will be broken when you add perturbation in your Hamiltonian system. Here, one quickly we can check one more case. Uh, uh, there is something Stark effect, which is also discussed in your lectures. If you see, so there also you have where we consider like what is that? Let's say that is when an atom is placed, any quantum particle or a quantum atomic system like placed. So atomic system is inherently a quantum system. So when it is placed uh, in some uniform external electric field, let's say that is E external, then the energy levels are shifted. So this is your Stark effect. So similarly, there would be something Zeeman effect. You would have learned that is when you place the same atom in some external magnetic field, you find this energy splitting. The same thing happens when you place it in some external electric field as well. So this is in external electric field, that is like in external magnetic field, which you see the Zeeman effect. So there are also like weak Zeeman effect and strong Zeeman effect, and there are also something like spin orbit coupling. So all these things are extensively discussed. You can check them out in your lectures. So here, like what happens when you place that atom? Let's say an hydrogen atom is there. Uh, say a hydrogen atom is uh, placed in a external field, that is uh, field, and it's and it's perturbing Hamiltonian. Initially, hydrogen atom has its own Hamiltonian. That is, you know, and it's, let's say, and its Hamiltonian is h equals to h0 plus h prime. So where h0, for a um, uh, for a hydrogen atom system, like your h0 is something p square over 2m. uh, then you have something plus alpha over r. So this is like your Coulombic potential. So this is your generally your Hamiltonian system for your hydrogen atom. So this is an unperturbed part. Now you have h prime, you have e external r cos theta. So yeah, e external is your field strength. That is uh, yeah, that is right. So for h0, for a unperturbed Hamiltonian, you can write your psi NLM. This is your uh, unperturbed uh, NL R YLM theta phi. So this is what you write down for your wave, for your energy wave functions or energy eigenstates of your hydrogen atom, and correspondingly you have some energy eigenvalues NLM. That is something, like this is, it is commonly written as minus 13.6 over n square. So this is in electron volt. So you see, for every NLM, you can see for every n, you have L going from uh, 0 to n, and for every L, you have M going from minus L to L. So suppose if you consider n equals to 1, like for what I'm saying, this is also a highly degenerate system. So you can see, for your energy eigenvalue only depends on n. So that means if you consider something first excited state, so first excited state n equals to 1. So first excited state would be n equals to 1. So energy eigenvalue is minus uh, no, first excited state is again, the energy eigenvalue is will correspond to n equal to 2, because n equal to 1 is your ground state. So um, for that is equal to minus 13.6 over 4. But if you see, this first excited state uh, uh, has three different states. I mean, first excited state energy eigenvalue is this, but if you write down the excited state, it would be uh, like your n equals to 2. That means your L can be 0 and 1. Yeah, it should be 0 to n minus 1. And your M could be again, uh, could go minus 1, 0, and 1. So you have many different combinations here. So it's very uh, completely a degenerate state. So like the all the possible combination would be something this. It would have side to 0, 0, side to 1, 1, side to uh, 1, 0, uh, side to so how this all happens, so maybe you can write down, let's say, uh, well, n equals to 2, possible L values are 0 and 1. Say n possible L values are 0 and 1. So let's take n equals to 2, uh, uh, or let's take, yeah, let's take n equals to 2 and L equals to 0. So for this case, your M should be only 0, because M can only go from minus L to L. Since your L is 0, M should be 0. So, so correspondingly to this, you will have psi 2, 0, 0. and again you have uh, if you take n equals to 2, l equals to 1, you have possible m values is uh, minus 1, 0, and 1. So you have psi 2 1 minus 1, then you have psi 2 uh, uh, 1 0, then you have psi 2 1 1. So you have four states. It's like uh, fourfold degeneration. So fourfold degeneracy, all of them have, I mean, this all of the states have the same eigenvalue. So again, if you put some kind of this kind of perturbation, you'll find you can again uh, degenerate this fourfold degenerate. You can break this degeneracy. You can break this fourfold degeneracy. Maybe again do something threefold, twofold, and particularly for this kind of perturbation, after you will evaluate. So I mean, if I like we can maybe discuss this again, we can work out this step by step. If you need it, like we can do that in the next week when we will meet again. But something if I write down, like for example what it would happen, so here also, I mean, the ground state is non-degenerate. First excited state is fourfold degenerate. So So if you apply the external magnetic field in in presence of external electric field perturbation, you can lift the you can break the degeneracy. You can break this fourfold degeneracy. Uh, so particularly this electric field perturbation. So this electric field perturbation actually, uh, this effect, this particular effect, or basically, uh, uh, yeah, let me this particular effect due to is caused due to electric field is also known as Stark effect. Also known as Stark effect. So the first fold degeneracy, if you um, uh, like I mean, you will find out. I mean, the first order correction is left first. Let me call this as again your first excited state. So your first excited state, will have uh, um, or your uh, yeah, this is like first excited state. So your correction would be something. Uh, Yeah, your first, your basically your corrections would be um, like, again you will construct a W matrix. So since your W metric will be a bigger one than the last case, because you have fourfold degenerate, so it would be a something 4 cos 4 matrix you will construct. Same way you have to consider, you consider this as your uh, psi A. This is a, I mean, yeah, you consider this as your psi A, psi B, then this is your psi C, and this is your psi D. Then you can, and your so your W would be again something psi H prime psi W A B, so psi A and psi B. So similarly, you will have W A B W uh, um, uh, B C and W C D. Then so on, you have W D D. Like you have all these four cross four entries, and from there you calculate the eigenvalues. So eigenvalues will basically give you the first order correction. Eigenvalues, they are first order correction in first excited state. So this will be basically, you will calculate the eigenvalue that would come out to be something 0 0 and plus 1 and minus 1. So you again see the fourfold degeneracy which was initially there, now it has reduced to uh, two separate twofold degeneracy. So here you can say the fourfold degeneracy is now broken into uh, two separate twofold, or basically broken into uh, one twofold degeneracy, one fold two degeneracy, and two distinct states, and two distinct states. So, so you can see that is what the Stark effect in hydrogen atom would give rise to this kind of effect in your first excited state. So the first excited state will break down its fourfold degeneracy into two distinct states plus two plus the other two states as twofold degeneracy. So yeah, so something you will find your I can finally conclude the last. So your first state, which is psi A, is something given as psi 200 200. It will have E uh, first excited state unperturbed, so plus 0. Then psi B is psi 2 1 minus 1. It will have E 0 first excited state plus 0. Then psi C will have psi 2 1 0. It will have E first excited state 0, plus if you calculate, you find out the eigenvalue which was giving plus 1. So there was also some initial factor. Let's say that factor is some that factor was something 3 3a or something. So that vector was something uh, 3a e external. So it would be something. So plus 3a e external times 1. So that is basically 3a external, and finally psi t is psi 211 e0 first excited state plus this will be minus 3a e external, right? So yeah, this is what the Stark effect in hydrogen atom. Yeah, that is for today. We are already over the time. So yeah, if there's any question or anything, please let me know. Maybe if we are already over the time, then we can discuss next time. So if you have any immediate question, please let me know. If anything not clear, uh, okay, probably we'll stop here. Then we meet again um, in the next week. So see you until then. So yeah. So yeah, thanks. Goodbye.